Morning, everybody. I hope you are fine. Are you fine? Thanks. Okay. Let's talk about determination in alpha and gamma ray spectrometry. I think that today you have to do this kind of exercise in the lab. Exercise at all, but let's see what happens. These are the contents of this presentation, how to determine peak areas, how to calculate activities, then something about the software. Which is in fact very simple. So you can calculate activity if you know measurement time, peak area, you know the emission data, and you know the efficiency. It's a very simple equation. However, I neglected corrections in this equation here. So, spectra. This is one of the spectrum taken from this presentation, publication. You cannot see, but you can later. Is the experimental data. Red one is so-called baseline. Let's look at this peak here. Determine the baseline. I mean, red or green. Complex, sir, because from my point of view, both of these are okay. You have to. Typically, this axis is logarithmic, so there is usually difference what is the baseline in principle. However, if the peaks are small, it might be large. In alpha spectrometry, there is no baseline in practice. And counts, for example, counts here can be taken into account for this nuclide, which is radium something, 226. What is an advantage of alpha spectrometry is that when radiochemical processing is done, and especially radio element separation, then the spectrum is very easy, very easy. So in this case, no radio element separation has been done because there are radium, radon, and polonium. So this is an example for uranium-235 and different enriched level. This is energy axis here. This is X-ray region coming. That peak shapes doesn't depend very much on the source characteristics. But in alpha spectrometry, characteristics is source characteristics is very, of course, the peak shape depends on the energy a little bit, but not very much. Baseline may change depending on the activity of the source. And some other things too. Right. This is one example. There are 3 nuclides which are curium. These nuclides here, here, here. At the very right side of the spectrum. Would you take this part into account in the area determination? Yeah, no. Because these are generated by soft photons, X-rays, perhaps gammas, electrons, positrons, etc. Area. Would take this part into account in peak area determination. Well, yes, maybe no. Depends how you do the peak area analysis. I will explain this more soon, but if you do region of interest analysis, as you did yesterday in the lab, then you cannot do that. But if you do peak fitting, perhaps then. Let's look at the basis of peak area determination. So there are 2 basic or main approaches, so-called ROI, region of interest, and peak fitting. In this method, you simply determine left side of the peak, right side of the peak, and the software automatically gives you number of the count. Or baseline here, not background. Background is a little bit different thing. What about peak fitting? Peak shape, which is practically Gaussian, as I explained yesterday, but there are some changes that can be taken into account. In this case, I have taken so-called step function into account because the base here is higher than the baseline here. Both of these methods are or can be applied in alpha and gamma ray spectrometry. In general, this ROI method is okay if you have individual peaks. But peaks like this is 186 peak, so there is either or both 5 and radium-226. In principle, you can use peak fitting method in this case. However, they are so close to each other that practically it's in this case not possible. an alpha spectrum in which there are two main nuclides, americium 243, 241, a little plutonium 2. So, how to determine the left side of this? You have to remember that in alpha spectrometry, the situation is usually that all these peaks are summed together. Because usually radio element separation is done. So it's not very useful to analyze the areas of these individual peaks. Here. If you are using peak fitting method, you have to know the peak shapes. Then it's possible. This is one example in our software known as Unisampo Sama. So it has in fact two softwares. Unisampo software search peaks. That's it. This shaman code, it identifies the peak. It's a very, I think, very high-level software. Although the interface is not very good. But in this case, this is 180 again. The software doesn't know that there is in fact two peaks because they are so close to get together. But software also plots automatically this baseline. And I can see, and you can see that, okay, there is something wrong here. So I can manually insert a peak here and do calculation. Okay. In this case, I added radium-226. Just an example. Spectrometry, the ROI method may be impossible to apply, and fitting is necessary. Yesterday we looked at this spectrum from nuclear bomb particle. What about this spectrum? It's quite difficult to analyze. It was obtained from this depleted uranium penetrator. This ammunition was used in Gulf War. So it's quite difficult to carry, but it is possible to determine activity ratio. Determine activity, we need to know peak area, but in these cases it's not possible because this peak continues there down, but we cannot detect down to zero pulses. An activity ratio. Into account this plateau and this plateau. I think that I already showed you this one, so nuclear bomb particle again. Operation with German scientists from Karlsruhe Research Center. These are uranium particles of diameter about 1 micrometer or so. So they are pure uranium, nothing else. In the case of processed samples. There are several mathematical ways to fit the peaks. However, there is none for these sources in general. To fit also this kind of spectrum. This is residual difference between the measured uranium nucleus. I think this is a simulated case, and there are three nuclides here. So it is Gaussian, and then there are, in this case, three tailing components into account. Then you can really take all account when you determine areas, peak groups. The what about this is normally quite normal case in environment because activities are quite often very low. So the number of peaks counts is very low. Okay, this is just an example containing same nuclides as in previous slide. You can see that there are three peaks, but how to determine peak shapes very accurately for peak tail. So it's sometimes radiochemical sample process. Not always, of course. These are the pictures from our software in gamma spectrometry. So efficiency, peak shape, and energy calibrations must be correct to obtain correct results. So in this case, there is a peak shape calibration. This is energy, this horizontal is peak shape as a function of energy. This is energy difference between linear calibration and true calibration, which was in this case second order polynomial. This is efficiency calibration that I showed you yesterday. We can get correct results. Take an example of an activity determination. Let's assume that we have radiochemically processed source having these nuclides. Data acquisition time, weekend, 3 days. This is seconds. Efficiency by using RC program. Area of this source diameter, source to detector distance, this, and the calculation is very rapid. Let's put this In addition to the data in the need to know the emission yield, which is obtained from the library. And in fact, one, if you look at the data. Not gammas. Decay corrections in this example because the half-lives are so long. Okay, as an example, these are the number of counts in these peaks. If you substitute number of counts, for example, in case of plutonium-230, alpha yield and efficiency, I got this one, 0.77 becquerels per sample. Very easy calculation. Very easy. But you have to know peak area exactly and efficiency exactly. So these two are for determining this. In our how to use tracers.
Amount of recovery that we are getting after the process.
Yes. Indeed, because chemical processing is very challenging. You never know how much, for example, polonium you get from the source. In this case, I contacted to you. They gave me these plutonium isotopes. You perhaps know that plutonium-39, 240, they are strongly overlapping, very strongly overlapping. They for the source, but they didn't told us the activities. So my task was to determine the activities, and without traces. I made a measurement which is like this. Then I used our fitting software. In equilibrium must be always accounted for in the analysis. This uranium chain, these two are important. This part here and this part here. As I explained previously, we do vacuum packaging of the sample. You do put some glue or something so that the beaker is as tight as possible, because radon very easily goes out from the beaker. That's the point. And if the waiting time is 5 times, 6 times this, 3 weeks typically, then we can say that this nuclide, this nuclide, this nuclide, this, and these two, they are in equilibrium. Same thing holds here, but there is a problem. In some cases, I have noticed that, for example, plants may absorb thorium much more than uranium. So in original state of the sample, there may be no equilibrium. So there is no easy way to directly calculate the uranium-238. You have to assume equilibrium, but the point is this waiting time, decay time. So if you put the sample into a beaker, tight beaker again, and wait 6 months, as Avan has explained yesterday or day before, then there is an equilibrium. This is thorium decay series, and I have here 3 questions regarding thorium-228. It's difficult to determine by using gamma ray spectrometry. Do you have any ideas why? All right. Now, how it goes here. Thanks. Sorry, I'm very clumsy of using these. So you can see the energies of thorium-228. Okay, these are okay. However, this peak is very close to the lead X-rays. Sorry, this text is in Finnish because this is I made this text several years ago for my colleagues so that we do analysis always at the same time. So I collected information of each natural radio element and checked that there are no peaks close to the relevant peak. So in this case, the emission probability is 1.22%, which is very small. And in addition to that, there are less X-rays. These peaks here, emission probability is very low, and lot of other nuclei present. So we cannot analyze thorium-228 as such. Okay, question number 2. It is, so, do we need a vacuum packaged sample to determine 228 thorium on the basis of radium-224? Do we need? Okay, there are 2 options. Yes, yes or no, please. Yes, raise your hand. Do we need? What about no?
Does 234 radium give a peak? Give a peak, a gamma peak?
I mean that because 224 radium, it's quite easy. Let me show this again. And let's go. This is an example of radium-224 determination. It's this yellow peak here. And we can use this peak, at least in our case, we have quite good analysis program. So it's possible. But the question is, do we need vacuum packaging in this case?
No.
You say no? What do you say?
No.
All right, let's go back. Oh, so yes, the answer is no. Why?
Because it's not a gas.
Yeah, both are metals. They do not escape from the beaker. What about question number 3? Did you got this point?
Can you repeat your answer?
Sorry, I have to go here.
Can you please repeat your answer? Why it's no?
Okay, let's. Thank you for the question. It's very important to challenge me. So, let's go back. Because in this case, when we want to analyze radium-226, we cannot use it because its emission yield is so small and its peak is together with uranium-235. And it has practically only one peak. So we have to analyze its daughters. But then we must know the equilibrium. There is a problem here. There is a radon. And because of the long half-life, we must wait at least 3 weeks so that there is equilibrium between this, and this. These two are very easy to analyze. However, the beaker must be closed very well so that radon gas doesn't go out from the beaker. This is the case for radium-226. So the point is that this is the problem. It may escape from the beaker. Now, in this case, there is no gaseous, there is no gaseous nuclide between these two. So we can analyze radium-224 as such because nothing is escaping from the beaker because they are both metals.
Vacuum packaging not required.
It's not needed to do vacuum packaging in this case. We have to.
But we need to wait for 3-4 weeks to attain the equilibrium.
To be absolutely sure that there is equilibrium. Typically, there is equilibrium practically always. But to be absolutely sure, then it's good. Okay, one more question. And this is related also to the equilibrium. So, radium-228, this nuclide, it's also difficult to determine because it practically doesn't emit gammas, or very little. However, this nuclide emits many gammas, and very easy to determine. And its half-life is very short. So in this case, there is practically always equilibrium. But the problem is that, okay, we can determine activity of this radium on the basis of this, but this is difficult to determine, this one, because the emission energy is around 64 kilo electron volt, and the emission yield is very, very small. But can we assume that there is equilibrium between these three cases? Usually there is, usually. For example, if you want to analyze stones or rocks or these kind of things. However, what about the case if you are analyzing, for example, soil or sand? Water is coming from the sky, and it may happen that radium may dissolve in different way compared to thorium. So what we decided in Stuk that we do not report thorium except when we are analyzing rocks, stones, and some other construction materials. Because we are not absolutely sure that there is an equilibrium. Then we report only this one. And as I said to you before, all members of the decay series are in equilibrium, then all nuclides decay at the same rate. The point is that several processes, which might be biological, physical, chemical, geochemical, and other things, may influence the equilibrium. And this is very important to understand this. Some slides about analysis software. There are some tools for generating alpha or gamma ray spectra, but not many. I showed you yesterday this ASI software. This is a tool for alphas. Now remember that to generate gamma spectra or alpha spectra, not to analyze. So there are high-level generators that are based on full Monte Carlo simulations. This means that practically all radius, all interaction phenomena are taken into account in the calculations. These are the examples of these programs: MCNP, GEANT4, EGS. There are, of course, some simplified codes, such as this one. What about the analysis of software, not generating the spectra? So one example is gamma vision and alpha vision. These are from Ortec. Prospect is a software package for data acquisition and low complexity analysis for gammas. It's a Mirion software. GSA is an open source open source software for gammas. Jenny, you have here, it is for alphas and gammas, as well as Apex Gamma and Apex Alpha. In Stuk, we are using Unisample Shaman program, which is running in Linux. But there are several other programs too.
Is Unisample Shaman open source?
No, no, unfortunately. In Stuk, we have developed these two software for alpha spectrum analysis because I don't like this ROI analysis. It is simple in many cases, but in difficult cases it's not. So we developed two different software, ADAM and ASI plus fitting, so we can analyze these kind of spectra. Well, if somebody wants, we can send, but this is operating in Windows, this in Linux. But this is it. Do you have any questions, comments?